Hi everybody. Today I am going to discuss about how to create or generate a exponential form of a complex number. So to do this, first we have to understand about Euler's relations. So to get the Euler's relations, I need to use power series expansion. So power series for e to the power x, we know it is e to the power x equal to 1 plus x square by factorial 2 x cube by factorial 3 dot dot dot. So this is the power series for e to the power x. Now this e to the power x, this x equal to, we will provide it as a, replace it as a j theta. So of course this ex, it will take the form like this, e to the power j theta. So the series will be changing. In place of x, we have to put j theta. So it takes this form series. Here you can see j theta to the power 4, j theta to the power 3. Accordingly it is done the way it is, only the thing is x equal to j theta. So this is the series for e to the power j theta. So let's move in the next slide to see what we will do next. So same equation I brought here, same series. Here we need to put the value for j. So we want to make a table. As we know, j equal to square root of -1. So we have to find the value for j to the power 0, j to the power 1, 2, 3, j to the power 6, j to the power 7, because all this term will appear here. So as we know this, so once we replace all this, it takes the shape as this. E to the power j theta equal to 1 plus j theta. Here look at, I put only theta square. So j square gone. Why? Because j square equal to -1. So I put here minus. Again, if you look at here, j theta to the power 5. So j5, j, why j? Because here compare this position, j to the power 5 equal to j. So I replace it by j. Again, here also j to the power 7 equal to minus j. So look at here, j to the power 7, I put minus. That's why here minus. So this is the way we got this e to the power j theta as this one. Now question is, here there is a one important point is, we can make it two types of group here. One is with the power with the even number. So look at 2, 4, 6, 8. But here power is 3, 5, 7, and all 3, 5, 7 power, it has j. Look at j here, j here, j here. So we have to take out j as a common. So we got one series here, another series here. So these two series, we have to replace it by sine theta and cos theta, because next slide we will see. This even number power, it is nothing but cos theta. And this one with odd powers, it is sin theta. And there is j. And already we know e to the power j theta. This is the Euler's relations. And if we put here minus, so its relations will be with here minus. So using power series expansion, we got Euler's relation, these two. And we will use it in our next slide. Polar form of a complex number. Polar form means our z equal to r, angle theta. This r means modulus, theta means argument. And for Argand diagram, here we have taken the complex number and we plot a point here with coordinate AB, and this real part of this ZA, it is horizontal axis with real axis, and imaginary part B, it is vertical axis, we call it as a imaginary axis. And these are, it is modulus. How we can get that? Connecting this point and the origin. The distance we got, this is modulus. And making this line with the x-axis, angle created by this, it is argument. This is the line for modulus, and this line creates angle with the x-axis, I mean real axis, it is argument. Now let's move for exponential form, because this is polar form. So exponential form of a complex number, what you will do here? Here I will put this, use this triangle, because a equal to r cos theta, because we know that cos theta, it will be a by r, sin theta, it will be b by r. So easily we can write a equal to r cos theta, b equal to r sin theta. So we know our complex number z equal to a plus bj. So bring it here and replace this a and b. So we get r cos theta plus j r sin theta. Taking r common, we get cos theta plus j sin theta. Now you found this. In previous slide, we found this part as a Euler relation having relation with the exponential term. This is trigonometrical term on the right hand side, and left hand side it was with the, look at this part, it is e to the power j theta. In our previous slide we got e to the power j theta. This is exponential term, and right hand side was trigonometrical term in Euler's relation. So now this trigonometrical term, we replace it by exponential term. That is why I wrote here exponential form of a complex number. Because this is complex number, we replaced it to get this relation. I mean z equal to r e to the power j theta exponential form of a complex number. So in the next slide, we will do one example. Already we know from Euler's relation we got this. So we are taking example, say z equal to 4 plus 4j. This is the complex number. Now what is the modulus? Already we saw r. If we want to get r, we have to use a square root of Pythagoras theorem. For this right angle triangle, Pythagoras theorem, we have to use this value for a and b, a square plus b square equal to r square. So r equal to 4 square square root of 32. This is modulus. And this modulus, absolute z, means it will never be negative. And also, complex number lies in the first quadrant of Argand diagram. In this diagram, if you look at arguments, what actually it is? Theta equal to tan inverse 4 by 4. Because argument we find, this is the, theta is the argument. So we know tan theta, we have to get this by this, b by a. It is 4 by 4 because we are finding theta. So it will be tan inverse. So surely tan inverse 1, it means pi by 4. It is in radians. In degree, it will be 45 degree. Now, in exponential form, what you can do? We can bring this number here in this form and put the value for this one. Replace this one. Because this is also z equal to, this is also z equal to. So we can write easily z equal to r means square root of 32 e to the power j, and theta already argument we know pi by 4. So we got this. This is our answer. Exponential form of complex number of this one. In exponential form, it will be like this. Z equal to square root of 32 e to the power j multiplied by pi by 4. That's all for today. Thanks for watching.